Aloha, this is Roger Brewer with the Hawaii Department of Health. This is a recording of a presentation I gave to the Environmental Council of States on September 30th, 2024. This is a fairly quick overview of Hawaii's approach to assessment of total PFAS risk. It's based on a presentation I gave at International Cleanup Conference in Adelaide, Australia, just a few weeks earlier. So in February 2023, I'd met with the ECOS group and gave a presentation on initial data that we'd collected in Hawaii's field study of PFAS. We went to 6 wastewater treatment plants and collected samples of influent, effluent, and biosolids. Also, we collected samples of leachate at 5 landfills, and we collected samples of AFFF contaminated soil at 2 sites and at groundwater at 1 site. We also collected samples of soil in remote areas of Hawaii to look for anthropogenic background levels of PFAS in soil, since we'd heard that they're everywhere. Just to jump to the last point first, at the 9 sites we went to, we did detect PFAS at 8 of those sites. At 1 site we detected trace levels of perfluorobutanoate. That was in some cliff areas right above a town, so it could have been some real data. Otherwise, not much in terms of anthropogenic soil background for PFAS in Hawaii that we've identified. Hawaii's published guidance on interim soil and water environmental action levels for PFAS. It was last updated April 24th. I'll be mentioning that guidance during this presentation some. You see the webpage. We're going to update it again in November of this year. We'll be adding toxicity factors and action levels for the compound trifluoroacetate or perfluoroethanoate. Also in November this year, we'll be posting a report on our field study of PFAS associated with wastewater treatment plants, landfill leachate, and AFFF release sites. Also in November, I'll be giving a presentation, I plan to, on our field study, and that will be recorded and posted to our YouTube web station. For a general overview of PFAS basics, I usually recommend people review the ITRC's 2020 document. I think it's being updated continually on PFAS. It gives a good overview of the chemistry, use of PFAS, and general toxicity. In this presentation, I'll be talking about the total oxidizable precursor method, TOPS method. A good paper review of this approach or processing of samples is by Ate et al. 2023. There are a lot of papers out there. I like this paper in particular. It explains how the process works and the intent of the process in fairly simple English. One question that comes up in our group and with everyone I've talked to in the US and around the world really is, what do we do with all the data that we get? Because the laboratories are reporting a lot of compounds that we don't have toxicity factors for, and we know we're probably missing a lot of other PFAS related compounds in our sample data. So to jump to the end of our PFAS study, one of our conclusions is we divided PFAS compounds up into 3 different groups in order to assess total PFAS risk. So group 1 were the primary terminal endpoint PFAS. These are standard PFOS, PFOA, hexasulfonate and such that are reported through standard laboratory methods. So that's the first component of calculating total PFAS risk. Next, we need to come up with an approach to address risk posed by precursor PFAS. We refer to this as our post-TOPS PFAS data. And then the third group of PFAS we identified in the samples were a lot of ultra-short compounds, again, lacking toxicity factors, lacking laboratory methods to identify them all. And we refer to this as our excess fluorine PFAS, and I'll explain this in more detail as we go through the presentation. We focus on non-cancer hazard for assessment of risk, and this is intended to protect developing children and pregnant mothers. We've been working with some epidemiologists, toxicologists, and in general, they have a higher confidence in the non-cancer toxicity studies and toxicity factors than the cancer studies. Cancer risk can be assessed separately for individual compounds like PFOS and PFOA. But based on our discussions, again, with toxicologists, epidemiologists, the general thought is that protecting against non-cancer hazards posed to developing children and pregnant mothers will also be protective of longer-term risks to adults. Let's go through these three groups of PFAS then. The first group, the group that gets reported by the laboratories, at least for the terminal endpoint compounds, is fairly simple. We've compiled toxicity factors now for 18 of the terminal endpoint PFAS compounds. These are basically fluorinated aliphatics. It's a simple way to look at it. We're also, as I mentioned, currently working with epidemiologists, toxicologists to develop toxicity factors for perfluoroethanoate, which is the proper name. The more common name in chemistry is trifluoroacetate. We should have that by the end of October of 2024. So in this summary here, I've noted the 18 different terminal endpoint PFAS compounds. And also we have toxicity factors for, and also note the risk-based action levels for soil based on residential exposure and risk-based action levels for drinking water or tap water. One thing you'll notice, the long chain compounds are highlighted in yellow. You see the numbers here, these action levels for soil and water are much lower than the ones in green. The green are the short chain PFAS compounds. Then in the blue, the only two of these listed here, these are the ultra short compounds. Toxicity of these compounds seems to be similar to the short chain compounds. Now, for trifluoroacetate, the only toxicity factors we found so far were published by a group in Germany. In that case, their drinking water action level, just to put this in perspective, was 60,000 nanograms per liter, so less toxic even than the butanoate. We say these are less toxic, these short chain compounds, but we've mentioned in other presentations, these compounds have similar toxicity to compounds like hexavalent chromium, benzene, DDT, TCE, PCE, PCBs. So they may be less toxic than long chain compounds, but they're still, I think anyone would agree, they're toxic. But we have toxicity factors for these compounds. If we have toxicity factors, we can develop action levels, and we can use those to assess risk. The problem comes with the precursor compounds, and this is where you hear there could be thousands of them, or depending on who you talk to, even millions of them. It's an example here of a precursor compound called 6,2-fluorotellumer thioamidosulfonate. It's the most common PFAS compound used in aqueous firefighting foam since 2005. It's not that complicated when you think about it. It's the parent PFAS. You could think of it as a heptanoic acid. It's this fluorinated heptane. So you have your 6 fluorinated carbons for heptanoic acid with the hydroxyl group attached to the end. So to create a function, to create 6,2-fluorotellumer thioamidosulfonate, you just add a big functional group on the end of this, and you have this new compound. So the problem is, even though this is the dominant PFAS compound in AFFF since 2005, toxicity factors aren't widely available. I think Hawaii is the only state that has published any. And that doesn't really matter because they're not reported by current laboratory methods. And so if you're testing for risk associated with spills of modern AFFF, anything after 2005, then you're probably underestimating the total risk posed by that contamination. This is particularly true for soil, as we'll show later. How do you address all these precursor compounds? This is the intent of the total oxidizable precursors method, or TOPS. This is used to simulate metabolism of precursors and then estimate precursor mixture toxicity. The way this approach works is the sample is heated with an oxidizing agent under alkaline conditions. I think the pH can be up to 12 or something. What happens is it strips these functional groups from the PFAS and leaving the terminal endpoint compound behind. I like to think of this as pruning a tree. So on the bottom here, if you see the tree, think of the small branches and the leaves as the functional groups. What TOPS does is kind of prunes that tree, removes the functional group, and then you can see the core element of that PFAS compound, the terminal endpoint PFAS. It's PFOS or PFOA or short chain PFAS compound. So what this does is identifies the presence of previously unreported ultra short, short long chain PFAS compounds in a sample. And this final terminal endpoint product mixture, minus your pre-TOPS mixture, is assumed to reflect the metabolic products of the original precursor compound mixtures. And this seems to match up pretty well with studies of natural degradation of testing with precursor compounds. Again, we use this to assess the overall toxicity of precursor compound mixtures. We'll look at some data for this later on. So it doesn't exactly mimic what happens in your body, but the end result seems to mimic that. There are a number of papers published on this. We worked with Dr. David Sedlec and other people at researchers at UC Berkeley and other places around the US to understand this approach better. This is an example of data testing soil that was impacted by modern AFFF. It's in one of the sites that we investigated. This occurred in 2022. The responsible party very quickly went out and excavated and removed, disposed of obviously impacted soil. We went in with our group and collected a 45 increment, 2 kilogram multi-increment sample from the bottom of the excavation and the sidewalls of the excavation. I always have to throw this in, if you're familiar with our work in Hawaii, is we really have to stop collecting grab samples at sites. I always think every revolution needs a slogan, so we say stop the grab. But we've demonstrated in the field, and a lot of people have for the last 40 years now, that grab samples aren't reliable. Move the sample point over a few inches, a few feet, you can get a totally different number. The laboratory tests a different spoonful or pinch of soil from the jar that you sent them, they could get a totally different number. So just as a side note, we have lots of presentations on our webpage and real detailed guidance on how to collect multi-increment samples. And moving on from that, in this case, on the bottom, these pie charts show the difference in the pre-TOPS data and the post-TOPS data. So the pre-TOPS concentrations, this would be the concentration of total PFAS reported by the laboratory using the standard EPA method. We're using SGS laboratories for most of our studies. This would be SGS method, MLA 110, 144 micrograms per kilogram. So we thought we saw this. While they did a really good job, got in there, excavated contaminated soil, left a trace in place, but not that much. Now I was talking with the laboratory chemist, and he said, yeah, but you know, you missed most of what was in there in the sample. That's when he explained to me what precursor compounds were, and that the AFFF, the modern AFFF, is primarily composed of 6,2-fluorotelomethylmethosulfonate, which they don't even report at the laboratory. They can see it in their chromatograms, but they can't report it. And you can see that after they ran TOPS analysis on it, it stripped off the functional group from that compound and left these terminal endpoint compounds, the pentanoate, butanoate, hexanoate, which is what you see in other studies on degradation of this precursor compound. And the concentration of total PFAS in the soil sample was actually, in this case, 500 times higher than what the laboratory reported based on non-TOPS sample processing. So this just emphasizes the importance of getting TOPS data, especially for your solid samples. We see the same thing happening in biosolids as we do for soil. Not so much for water samples, liquids. We'll look at that in a minute. So that was the solids. One thing we learned dealing with testing of liquids with water samples, and all of our samples of wastewater, landfill leachate, AFFF, groundwater, if we sum up the total concentration of PFAS reported by the laboratory and then compare that to the concentration of total organic fluorine reported for the sample, the total organic fluorine can be up to 10 times higher. So there's a lot of organic fluorine in these samples that aren't attributable to individual PFAS compounds. The leachate from landfills is a little bit less, but there's still quite a bit of we call excess organic fluorine in the sample, not attributable to the reported PFAS compounds. Same thing in AFFF groundwater. The concentration of these PFAS compounds associated with the total organic fluorine in the water is significantly higher than what the laboratory reports for individual compounds, and you sum those up. So we have to come up with a method to address these compounds. Now we got non-targeted analysis data for the compounds, and they pretty consistently show that all this excess fluorine, organic fluorine, is associated with ultra-short compounds in the water. We discussed this in other presentations. It's partial breakdown of the precursor compounds and of the PFAS compounds themselves. I think of it as PFAS debris, 2 and 3 carbon fluorinated compounds in the water. How do you deal with all this excess fluorine? This is where, in our approach, we only have toxicity factors for these ultra-short compounds for perfluoropropanoate. So under our approach, we use propanoate as a surrogate for all the excess fluorine-related PFAS in these samples. To the estimated or excess organic fluorine, it's assumed all the excess fluorine has the same toxicity as the propanoate. So what we do is we adjust the excess fluorine concentration to reflect the equivalent concentration of propanoate in the sample. And then we can compare this to our action levels, risk-based action levels for propanoate, either for soil or solids or for drinking water. And when we do this, we can calculate a hazard quotient, so a standard risk assessment approach. This is fairly straightforward stoichiometry to do, to calculate a concentration of excess fluorine-related PFAS in a sample make an equivalent concentration to propanoate. You take your excess organic fluorine concentration and then multiply it by the molecular weight of propanoate divided by the atomic mass of fluorine times the number of fluorines in perfluoropropanoate. This gets simplified down to your excess organic fluorine concentration times 1.73. We'll look at that as an example later on. And you see our action levels for the propanoate here. They're fairly high. Again, it's the ultra-short compound. It's much less toxic than the long chain compounds. So now we have three different methods in. We have a method for each one of these three different groups of PFAS that we've identified as part of our study. So your total PFAS risk, again, is equal to the sum of the risk posed by the primary terminal endpoint PFAS. That's what the laboratory would typically report to you, PFOA, hexasulfonate and such, plus the risk posed by these precursor PFAS, which we refer to as post-TOPS PFAS, plus the risk posed by these ultra-short PFAS compounds, which we're referring to as excess fluorine or excess organic fluorine PFAS. Again, we focus on non-cancer risk. We actually have action levels for cancer risk, but again, the non-cancer risk action levels are lower and take precedence. Let's look at some examples. We'll just look at one example. This is some biosolids that were collected at a municipal wastewater treatment plant. Well, one thing to keep in mind with the biosolids in our study, these wastewater treatment plants, they don't receive significant leachate from wastewater treatment plants. And that's one reason why the total risk, as you'll see, is lower than what you would expect from sludge and biosolids from some type of industrial wastewater treatment plant. So first, look at the calculation of your primary PFAS risk for these pre-TOPS compounds. Here, this shows the list the compounds that were identified either in the pre-TOPS or post-TOPS. In the pre-TOPS analysis of the sample. So you see that PFBS, that's perfluorobutysulfonate, it's reported a concentration of 1 microgram per kilogram. Divide this by the action level. See, it's pretty high. You can calculate a hazard quotient where I just ran it out to 3 significant digits here. It's pretty much 0. So for each one of the compounds to assess risk, then you just divide the concentration in the sample by the soil action level. In this case, we're using residential action levels. These action levels based on a hazard quotient of 1. Then you sum up the hazard quotients for all the compounds identified, and that's a hazard index, a cumulative hazard index for these compounds. It comes out to 0.5. So when your hazard index is less than 1, then you don't have there's no significant health risk. When it's greater than 1, then you'd want to look at it in a little more detail. Work with a toxicologist, epidemiologist, see if it's really a significant risk. In this case, the hazard index from these pre-TOPS compounds, your standard list comes out to be 0.5. So if we only looked at these data, then we would think there's no significant risk from these biosolids. Your kids can play in them, no problem. That was the first group of PFAS. Look at the second group. These are the precursor related PFAS or post-TOPS PFAS. So now we've oxidized the sample using the TOPS analysis. The way we assess risk now, that we need to calculate the concentration of these terminal endpoint compounds associated with the precursor compounds that were broken down using TOPS. To do this, we subtract the pre-TOPS concentration of the compound from the post-TOPS concentration of the compound. So looking at butysulfonate again, initial test, pre-TOPS report a concentration of 1 microgram per kilogram butysulfonate in the sample. After TOPS analysis, they report a concentration of 8.2 micrograms per kilogram in the sample. So subtract 1 from 8.2, 7.2 micrograms per kilogram of the butysulfonate are associated with the breakdown of the precursor compounds. So we do that for each one of the compounds, subtract pre-TOPS from post-TOPS. That gives us a concentration of what we're referring to as the precursor TOPS PFAS. And you can see it's, in this case, the TOPS method, after TOPS processing, it broke down whatever the precursor compounds were in this sample to mostly these short chain compounds, butanoate, pentanoate, hexanoate. They make up the majority of the precursor TOPS compounds. Now we can sum up the precursor TOPS PFAS, adds up to 382 micrograms per kilogram. So compare that to our pre-TOPS concentration of PFAS in the sample, 26 micrograms per kilogram. If we only looked at the pre-TOPS concentration without TOPS processing, we would have underestimated the total concentration of PFAS in the sample by more than 90%. So now we've calculated the concentration of precursor TOPS PFAS in the sample. And these are the terminal endpoint compounds generated after TOPS analysis. So you see for butysulfonate, 7.2 micrograms per kilogram. Now we do treat this the same way we did the primary PFAS compounds, divided by the action level. That gives us a hazard quotient. You can see for butysulfonate, it's still really low. 7.2 divided by 16,000 doesn't even show up as a hazard quotient, out to 3 significant digits. So we do that for all the compounds that were identified in the sample, divide by the action level, and then sum all these, some of the hazard quotients up, and that gives us the total hazard index for these precursor PFAS compounds. In this case, it's 1.0. So remember, pre-TOPS PFAS hazard index was 0.5. Now we have to add 1 to that because we're including the second group of PFAS, and the total hazard index is now 1.5. So if I only looked at the pre-TOPS compounds, we would have underestimated the hazard index, or the risk, by 3-fold. So that was the second group of compounds, example, the biosolids. So these same biosolids now we're going to look at the ultra-short compounds we identified using total organic fluorine. So we have to calculate how much excess fluorine is in the sample. We do this, we calculate the concentration of organic fluorine associated with the identified compounds. It'd be the first step, just the predicted total organic fluorine. So for the butysulfonate, we know it has a molecular weight of 299, has 9 fluorines in it. We had a post-TOPS concentration of 8.2. So this should have included all the butysulfonate in the sample. So to calculate a concentration of organic fluorine, again, it's just simple stoichiometry. You take the concentration of that compound identified in the sample, multiply it by the atomic mass of fluorine times the number of fluorines, and divide that by the molecular weight of the compound. So in this case, we would predict a concentration of organic fluorine associated with the butysulfonate in the sample of 4.7 micrograms per kilogram. In general, to estimate how much organic fluorine would be associated with a specific compound, multiply it by 60% or so. That'll put you in the ballpark. It's usually 60 to 70%, maybe 50%. So we do that for each one of the compounds identified after running TOPS analysis on the sample, calculate the predicted concentration of organic fluorine associated with that specific compound, add that up, and we get the total predicted organic fluorine concentration for the sample. In this case, it was 265 micrograms per kilogram. And we compare this to the measured total organic fluorine reported by laboratory of 842 micrograms per kilogram. So subtract the predicted from the measure, that gives us an excess organic fluorine of 577 micrograms per kilogram. and based on non-target analysis reported by the laboratory, then these compounds are mostly associated with ultra-short compounds in the sample. In most cases weren't reported by the laboratory. So now we have a concentration of excess organic fluorine in the sample. We can convert that to an equivalent concentration of perfluoropropanoate just by multiplying it by 1.73. Divide that by our hazard quotient for perfluoropropanoate, 5,100 micrograms per kilogram, and there's our hazard quotient or our risk associated with all this excess fluorine-related PFAS in the sample, 0.2. So now we looked at approaches for each one of these three groups to calculate risk for individual groups. We just add them together to calculate total PFAS risk. So we add the pre-tops PFAS risk for the primary PFAS in the sample, plus the post-tops PFAS risk. These are the precursor compounds, plus the excess fluorine PFAS risk. And we get a total hazard index now of 1.7. Hazard indices are rounded off to a single digit for assessment of risk, so this would round up to 2. And this is still not that high. If it's less than 3, it's usually not a significant health risk. If you're over 1, you want to look at it in more detail to make sure you have all the exposure. But if we'd only looked at the pre-tops PFAS, the risk posed by these primary PFAS compounds in the sample, we would have estimated a hazard index of 0.5. In reality, looking at this approach and looking at all cumulative risk posed by all the PFAS in the sample, the risk is actually 4 times higher. Again, still not that high. This seems to be very typical for all the biosolids samples we tested, is they don't really, the PFAS in the samples or in the biosolids in general doesn't pose that significant of a health risk if it's biosolids from municipal wastewater treatment plants that don't get a lot of landfill leachate. But that probably seemed a bit complicated. I think from a risk assessment standpoint, it's fairly simple, but it's hard to put all together. So what we did is we used Excel and prepared what we call a total PFAS risk calculator. It's pretty simple to use. Again, I'll go through an example with biosolids. Step 1 is you would input your sample information, the project name, sample ID, the date, this general information you put in here, and then the other thing you want to put in. Step 2, you select whether it's a solid or a liquid. What this does, it's going to compare your input data to either our risk-based action levels for soils or risk-based action level for drinking water toxicity. In step 3, you select your exposure scenario. This only applies for the soil. Is it a residential site or is it a commercial industrial site? And this again selects the appropriate action levels to compare the data to. So that's the first step, pretty simple. Second step, you go to the next worksheet in the calculator, and at the top you input your extractable organic fluorine concentration. In this case is 842 is what the laboratory reported. Then we're adjusting that because the excess fluorine mass adjustment factor. This is just going to adjust that excess fluorine concentration to whatever surrogate you want to use. In this case, we're using propanoate, so we use the adjustment factor of 1.73. So that's a default, put that in there. In the next step, you'll input your pre-tops data reported by the laboratory for these terminal endpoint compounds, and you input your post-tops concentration of the same compound. And when you do this, then in some other worksheets, it's subtracting the pre-tops concentration from the post-tops concentration. It's calculating a concentration of these primary PFAS compounds associated with precursor compounds. Then it's comparing those to action levels again, this second group of compounds, and calculating a hazard quotient. This is all done in the background, the worksheets you can look at, but you don't have to do anything. This is all you do then. You input your data, go back to the first page after you've input the data, and the spreadsheet is calculated a total PFAS risk. So it's calculated a hazard quotient for each one of those 3 groups of PFAS. The primary pre-tops PFAS, your precursor post-tops PFAS, and your excess fluorine PFAS. Then it sums them up, and there you see your total PFAS hazard index of 2. It's greater than 1 again. So it just says, note will pop up saying additional review of potential health risks is required. So that was it. It's actually fairly simple. I think once we get it in a spreadsheet form and looking at these three groups of compounds, it helps us avoid missing potential risk associated with PFAS contaminated sites. These are some summary notes from our observations. These will be discussed in the report we published in November. For the solids, these are the soils and the biosolids, and the TOPS processing in all cases, definitely in all cases of the biosolids, and for any post-2005 AFFF releases in the soil, identified significant additional short chain and long chain precursor compounds. These were in the biosolids. And in the soil, again, you're breaking down that perfluorothioamidosulfonate compound. So it's definitely important to run TOPS on solid samples, or you could be missing most of the risk. The total organic fluorine, even our biosolid samples, we saw a lot of additional ultra-short compounds in the biosolids. They're again being missed by the standard test. These are identified with a total organic fluorine test. Some summary notes here for municipal wastewater treatment plant biosolids. It's the precursor compounds in the samples we collected that drive risk. It's not these primary terminal endpoint compounds. It's all these precursor compounds, a lot of them complex mixture metabolites in the biosolids. So it's important to run TOPS on biosolid samples and account for these precursor PFAS in the sample. For AFFF impacted soil, for pre-2005 AFFF, this is when they were still using PFOA or PFOS, then the primary PFAS drive risk. So if you ran TOPS on these samples, you're not going to see a big difference because they've always been using these primary PFAS. For the post-2005 AFFF, then you don't see these primary PFAS in there anymore. It's all these precursor compounds, especially that perfluorothioamidosulfonate. So it's pretty critical. You run TOPS on the sample to identify that. And it's the precursor compounds that drive risk, not these primary PFAS compounds. For the liquid, when we ran TOPS processing on all of our water samples, we didn't see a big jump in the total concentration of PFAS in the sample. Actually, most times they went down. And this is because even with pre-TOPS PFAS, your standard analysis, they include some precursor compounds like the 5,3-fluorotelomere carboxylate. When you run TOPS on that, it's breaking off the functional groups and you're retesting the sample. And the concentration can be lower because you've lost that functional group for that compound. So TOPS doesn't make a big difference for looking at liquids as far as potential risk goes. The total organic fluorine for all of our water samples will identify significant additional ultra-short compounds in the water, where it dominates the wastewater, leachate, and AFFF-impacted groundwater. So it's important to use total organic fluorine to identify these compounds in the impacted water. For municipal wastewater treatment plant effluent, because most of the PFAS we saw in the effluent were these short chain, less toxic compounds, but they were so overwhelmed by the massive ultra short compounds in the effluent that these ultra short compounds actually drove risk over any primary PFAS in the sample. I'm guessing that's going to be pretty common, so it's important to use total organic fluorine and other methods, maybe non-target analysis, to look at wastewater treatment plant effluent. So there's a lot of ultra-short compounds in there, our experience. Landfill leachate, again, there's lots of ultra-shorts in landfill leachate, but the landfill leachate we looked at in the 5 or so landfills where we collected samples from, they all had PFOA or PFOS or hexasulfonate or something in them. Because they're so much more toxic, even though they were much lower concentration, they tended to drive risk over the ultra-short compounds. So the ultra-short compounds can add to the risk. And in general, it's these primary PFAS compounds driving the risk at landfill leachate, again, just based on our sample data. Now for AFFF-impacted groundwater, now we only looked at one site, but we talked to people and other regulators and consultants around the country and other places for AFFF-impacted groundwater issues. And in the source area, it's even though there's still lots of ultra shorts, a lot of these small short chain ultra short PFAS debris right in the source area. It tends to be the primary PFAS that drive risk just because they're so much more toxic, the PFOS, especially the hexasulfonate. As you get in the more distal areas of the plume, though, we predict, we don't have any data showing this, that these ultra-short compounds, which are going to be much more mobile, would move out to the front of the plume, and they could drive risk out in the leading edges of the plume. It's something we haven't looked at. We don't really have any long plumes of AFFF contaminated groundwater in Hawaii. Just something we'd predict you'd probably see if you start looking, asking the laboratory to report the perfluoronoate and the trifluoroacetate, such for some of your groundwater samples in distal areas of source areas. And see what you find. Also get total organic fluorine data for those samples and see if these ultra shorts really are out there. That was a fairly quick overview of presentation we gave in Australia and in general of some of our early findings. Some of the ongoing research we're doing with people in the US and around the world really is looking at nature and toxicity of these apparent ultra shorts. All this excess organic fluorine in groundwater in particular, what does it mean? Do we really need to be concerned about it? We're also looking at leaching of PFAS from soil and biosolids and working with some groups on bioavailability of PFAS in soil and biosolids and uptake of PFAS into food crops where the land has been amended with biosolids or they're using treated wastewater for irrigation. And of course, you can't leave out vapor intrusion for anything, it seems. That's some groups are looking at that. So there's the approach we put together, I think, compiles a lot of good ideas from around the country. So is it perfect? Not at all. It's some quotes here. All models are wrong, but some are useful from George Box. I think it's a useful approach. We can improve it in the future. But as far as the amount of testing you need to do, I like the quote from John Maynard Keyes: "It's better to be roughly right than precisely wrong." So it's really important to get TOPS analysis for soil and biosolids if you're going to do that. Test those materials and assess the risk posed by those compounds. And for water samples, TOPS analysis can really give you some good forensics information on the sample, but it's especially important to get total organic fluorine and ask the laboratory to report ultra shorts as they can. So that was it. As I mentioned in the presentation, I'm actually semi-retiring from the Department of Health into November. I'll be working part-time starting sometime next year. So I have my email for the Department of Health won't be useful at the end of November, but I gave my Yahoo email on the front page, the opening cover slide. I definitely like to keep in touch with everyone. So thanks a lot for all the input, and I'm sure we'll be working on this for several years to come.